Good day, everyone. Welcome back to Physics 30. We're going to be going over lesson 2.4 today, which deals with electric fields. This is actually called Electric Fields Part 2, where we're going to be looking at field diagrams and also looking at calculating electric field strength due to multiple charges. I'll just remind you of the previous lesson's work where we talked extensively about fields in general, and then through a comparison between gravitational forces and fields with electric forces and fields, we were able to come up with these two formulas to calculate electric field strength. Both of these formulas calculate the magnitude of the electric field strength. The direction of an electric field is defined by the direction in which a positive test charge would be forced. We talked briefly about that in the previous lesson, but we're going to talk about it more extensively in this lesson. If you do happen to know the charge on the source of the field and how far away from that charge you are, then you're going to calculate electric field strength using the formula on the right. And we're going to be using that formula a lot today. If, however, you happen to just know the value of a test charge and the amount of electric force it experiences, then you use the formula on the left. And I don't want to get bogged down in this, but if you take those two electric field strength expressions at the top of the screen and set them equal to each other, all you're going to end up with is a rearranged statement of Coulomb's law, which is at the bottom of the screen. And that, again, is something we talked about yesterday. So let's get started with today's lesson. We're going to be doing two things today: sketching electric field diagrams and then calculating electric field strength due to multiple charges. Yesterday, what we looked at doing was calculating electric field strength due to a single charge. And just to remind you, we did that by using the formula on the right-hand side at the top of the screen here. So some of these field diagrams are already given to you, but I want to walk you through drawing them piece by piece. Gravitational fields, and the symbol for gravitational field strength is lowercase g, and it's a vector. Gravitational fields are a result of a mass that is a source of a gravitational field. What I talk about in class very often is the property of matter that you require to produce gravity is mass. And mass always produces a field which will influence other masses put in the field, and we call those other masses a test mass. So if I were to put a test mass at, say, the top of this screen, it would experience a gravitational force towards the source mass. And that means that's the direction of the gravitational field above this source. If I were to put a test mass below, it would experience a force upward. If I put it to the right, it would experience a force to the left. I think you get the idea that no matter where I put a test mass, the influence, which is the direction of the field it's in, will always be towards the source mass. And that's why we say that this is the gravitational field diagram for a source mass. And this is something you would have been taught in Physics 20. So now we extend this to electric fields, but electric field diagrams are a little trickier because when you put a charge in an electric field, it may be attracted to the source of the field, or it may be repelled from the source of the field. And the reason for that is there are two types of charge. When we go back and look at this gravitational field, there's only one type of mass, and mass is always attracted to mass. So we have to come up with, for electric fields, a rule that we're all going to follow. I kind of liken it to us all driving on the same side of the road so we don't have accidents. We don't want half of the people in the scientific community using direction of an electric field one way and the other half using direction another way. So we have agreed on this idea that the direction of an electric field is the direction of the electric force on a positive test charge placed at various locations. So we are always thinking about putting a positive source into the field. So for a negative source charge, if I were to put a positive test charge above it, it would be attracted to it. And I sometimes will call that positive test charge an imaginary positive test charge. If I were to put that positive test charge below that negative source, it would be attracted, because positive is attracted to negative. And no matter where I put that positive test charge, and words are important here, I'm saying test charge, no matter where I put that positive test charge, it will be attracted through an electrical force to the negative source charge. And that means that's the electric field surrounding a negative source charge. If I were to change my mind and say, you know what, let's look now at an electric field diagram when we have the source of the electric field being a positive charge. Well, if I put my imaginary positive test charge, which I always use, above that source, it will be repelled. It will experience a force towards the top of the screen. If I put that positive test charge below my positive source, it will be repelled to the bottom of the screen. And I think you get the idea that no matter where I put that positive test charge, which doesn't really exist, it's just an imaginary thing I'm putting in different places in my mind to see the direction. No matter where I put that thing in my mind, it would experience a force away from the positive source. So this is why this is the electric field diagram surrounding a positive source. Now, what happens when we have 2 point charges creating an electric field? Well, I mean, I could just draw this for you, but I would rather not. I would rather you have some kind of understanding of what's going on here. So I take a positive test charge. Let's say I take this positive test charge and I decide to put it here. Well, that positive test charge that I've just put on the right-hand side of the screen is attracted to the negative source, and it's repelled from the positive source. But since it's so much closer to the negative part of this combination of source charges, since that imaginary positive test charge is closer to the negative side, Coulomb's law says the attractive force towards the negative will be greater than the repulsive force away from the positive. And for that reason, what we end up with is an electric field on the right-hand side of the screen that is in that direction. We could certainly use the same logic on the other side of the screen. If I were to put a positive test charge here, it would be both repelled from the positive source, the positive gray thing, and it would be attracted to the negative source. But because that positive test charge is closer to the positive source, Coulomb's law says that that force of repulsion will be greater. So this is another part of our electric field. If I were to put my imaginary positive test charge anywhere in this region, then it will be repelled from the positive source and attracted to the negative source, so it will have a field line that looks like that. No matter where I am on this line in my mind, the positive test charge will be forced to the right. Now, things get trickier when we start looking at other locations. If I were to put that positive test charge exactly halfway in between, then it's going to have 2 competing forces acting on it, exactly halfway in between, but up from the middle. And I don't want you to write anything just yet, because what I'm about to draw are not electric field lines. This positive test charge will be attracted to the negative and repelled from the positive. And assuming those 2 source charges are of equal amount of charge, these 2 forces will be of equal magnitude. I just want to clean something up here. These 2 forces will be of equal magnitude. And if you draw them tip to tail, what you end up with essentially is a direction of the net force acting on this test charge being that way. That red line is not an electric field line. And the reason it's not an electric field line is if I now take that positive charge, test charge, and I put it, say, here, you will now have 2 competing forces. So we have the direction of the electric field here being to the right. Now, what is the direction of the electric field at this new location? Well, it will be attracted to the negative, but it will be attracted greater to the negative, or with a greater magnitude because it's closer, and it will be repelled from the positive, but not by as much. And if you draw these two blue vectors tip to tail, what you end up with now is a direction of the electric field here being angled down because that one vector is longer. So how do we kind of draw a seamless electric field diagram that represents this? What we do is we draw the following. And if I were to ask you what is the direction of the electric field here, I'll draw these individual directions in green. It's this way. What's the direction of the electric field here? It's this way. And no matter where you are, the direction is following that red curve. Now we could go on and use the same kind of logic for a number of different locations. But now that you have a basic understanding of this, I think the diagram should kind of come together nicely in your mind. And in the end, you just have to know that this is what it's going to look like. It's going to look like that. We are also going to have field lines that come up like this, and down and then back up like this. I would say to you that less is better here. I don't think you want to start drawing a gajillion lines. It's going to look like this. It's going to come back down. It's going to look like this. It's going to come back up. And that's good enough. And I think in general you should recognize a couple of things. The field lines go away from the positive and towards the negative. And as you might remember from Physics 20, when field lines are closer together, the field is stronger. When field lines are further away, the field is weaker. So for example, in this region here, the field lines are quite far apart relative to in this region here where they're a little closer together. Bottom line, this is what it looks like. For the next couple, I'm not going to use that same logic and start going through the vectors. I don't think it's necessary. When you have two positive test charges, if you were to use that logic of the multiple vectors acting on the imaginary test charge, the multiple force vectors, and use them to get directions, what you would discover, well, this part should be pretty obvious, will be away from the positive because positive test charges are repelled from positive sources. And what you're going to discover is you will get curves that look like this. And again, I would really impress on you the fact that less is better. Less is more here. It gets pretty clunky when you start to draw much more than that. I will do this. I don't even like doing that. I'm going to leave it there. That's good enough. If you want to look at more detailed field diagrams, feel free to look online, but essentially that's good enough. Away from the positive. If I were to look at two negative sources, well, it would be identical to the one we just did, except the directions would be opposite. Because positive test charges will be attracted to negative sources. And you know what? At this level, everybody, it's not a university level course. We're not looking at a deep analysis of these. I think students in Physics 30 need to know that electric field diagrams show arrows that are the field lines or the direction of the field lines that go away from positive and towards the negative, and the closer the field lines are together, the stronger the field. I said we're going to do two things in this lesson. One is field lines and field diagrams, and the second one is finding electric field strength and direction due to multiple sources. So you're given this diagram where we have two source charges, and you're given some point in space x. And I think it's very important you understand this point x, there's nothing there. There is nothing here. It's just a point in space. Okay. What we are asked to find is the magnitude and direction of the electric field at point x. So why is there an electric field at x? Well, there's an electric field at x because the charge on the left would influence a charge put at x, and the charge on the right would influence a charge put at x. So there's an electric field there. Any charge put at x will experience some influence, and that's the definition of an electric field. So how do we do that? Well, we recognize, everyone, that there is an electric field at x due to the charge on the left. And I'm actually going to label these. I don't know if they're labeled in your notes. I don't think they are. I'm going to label this as source A and source B. And we can certainly calculate the magnitude of the electric field at x due to source A. And we can also calculate the electric field, the magnitude of it, at x due to B. And we're going to do so by using the formula we talked about yesterday, that the magnitude of the electric field due to a source charge is Coulomb's constant times the charge of the source over the distance squared. This will give us how many newtons per coulomb of influence there are at x. Now, when we calculate the electric field at x due to sphere A, or charge A, we're going to take Coulomb's constant, and I'm not going to write it down. We know what Coulomb's constant is. It's 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. It's K. And I'm also not going to worry about units here. We've talked about this in class numerous times. If you were ever given any kind of written assignment, or you're working in post-secondary on an assignment or a quiz or an exam where it's expected, then you're certainly going to put units. Times the magnitude of the charge, which is 45 microcoulombs, which is 10 to the negative 6 coulombs, divided by the distance in meters squared. So that's 0.27 squared. And we can calculate that number. We'll do it in a second. If we want to calculate the magnitude of the electric field at x due to B, we're going to repeat the process. We're going to take Coulomb's constant. We're going to multiply by the charge on B, which is 25 microcoulombs. And we're going to divide by r squared, which is 0.35 squared. Well, let's calculate those two, and then let's talk about how we're going to use them to find the answer to the question. I just want to get rid of this. I was just putting it there to remind you what the formulas are. Let's see. So Coulomb's constant, 8.99 multiplied by 10 to the 9 times the charge on A is 45 microcoulombs. Remember to use your scientific notation function. Don't enter times 10 raised to. That leads to errors. And then we divide by 0.27 squared. Double check before I hit enter. 8.99 times 10 to the 9 times 45 microcoulombs over 0.27 squared. So this electric field at x due to A is that number. I'm just going to park that there so I don't have to write it down. Now we're going to repeat the process, but it is 25 microcoulombs, and it is 0.35 We'll double check that. Coulomb's constant times 25 microcoulombs over 0.35 squared. We're in business. So this is the magnitude of the electric field at x due to b. Let's write these down now. So the magnitude of the electric field at x due to A is 5549383. And that's newtons per coulomb. And I'll leave it up to you to carry all the decimals if you want, but that's really not significant at this point, no pun intended. The magnitude of the electric field at x due to B is 1834694. 1834694 newtons per coulomb. I'm by nature a bit of a curious person, and when I compare those two numbers, my mind says, you know what, that second electric field strength is less than half of what the first electric field strength is. Does that make sense? And it does to me, because B is further from X than A, and B also has a considerably smaller charge than the charge on A. So these make sense. Now, when you were asked to find the magnitude of the electric field at point X, you're really asked to find the magnitude of the net electric field. These two source charges create individual electric fields of these magnitudes. What's the net electric field? Well, the net electric field will be what we get when we add these two together. But wait a minute here. What is the direction of this electric field? What is the direction? Well, we put an imaginary positive test charge here. It's not really there, it's just there in our head. We look over here at this charge, this is my eyeball, and I notice that it's positive. And then I say, well, which direction will this imaginary test charge experience an influence? And the answer is away from source A, because source A is positive. And what that means is that this direction is to the right. And then I ignore A and I cast my gaze over here at B, and I say, well, B is positive. B is also a positive source charge. And I say, well, now I look over at this thing in the middle. Oh, right, it's a positive test charge, and it's a positive source, so the electric field at X due to B will be away from B, and that means that this will be to the left. I mean, if we had to draw vectors on this now, this is the electric field at X due to A, and this is the electric field at X due to B. And those are the two vectors that we have to add together to get the net electric field. So how do you add vectors? You have to consider direction. If you're adding two vectors that are in the same direction, you simply add the magnitudes. That's not the case here. If you're adding vectors that are in opposite directions, then you subtract the magnitudes. Larger magnitude, in this case, 5549383 newtons per coulomb, minus 1834694 newtons per coulomb. And that will give us the magnitude of the net electric field there. let's see, I should be able to just grab these. I'm going to take the larger magnitude and subtract the smaller magnitude. So I'm getting 3.7 times 10 to the 6. Newtons per coulomb, and the direction here will be right because the larger electric field was to the right. And that's the answer to that example. The final example, number 5, is going to be done in the exact same way, except how we add those two vectors is going to change. First of all, if I were to put an imaginary positive test charge at P, it would be repelled from A. I better label these again. I'm going to call this A. I'm going to call this B. So if I put an imaginary test charge at P, and we're asked to find the net electric field at P, and I just realized there is a typing mistake here. There's a word that doesn't belong in this sentence. It says find the magnitude and direction of the net electric field at P due to the other two charges. Well, there aren't other two charges. There aren't two other charges. There's only two charges to begin with. So the word other has no place in this sentence. Find the magnitude and direction of the net electric field at P due to the two spheres, period. So this thing that I have drawn, this vector I have drawn over here, is the electric field at P due to A, and it's to the right because A is positive, so an imaginary positive test charge would be repelled from A. This vector that I'm drawing is the electric field at P due to B. Why did I draw it so much longer? Well, I probably didn't do it justice, but my instinct says it's going to be a greater electric field because it's closer to B than it is to A. Then again, B has a smaller magnitude of a charge. But I think that closer distance, that smaller distance, will more than make up for that loss in charge. It's not really important that you understand what I just said, I suppose. I'm just maybe talking out loud. So what we need to do is calculate the electric field at A. And I'm not going to write down everything in this example. Electric field magnitude is found by taking K times Q over R squared. I mean, by the time we've gotten to this point in the course, I don't think it's really necessary for us to write down everything. So I'm going to take K, which is 8.99 times 10 to the 9. I'm going to multiply that by 55 microcoulombs. I'm going to divide that by 0.12 meters, remembering to square it. I'll just double check that. Coulombs constant times the charge in coulombs divided by the distance in meters quantity squared. And I get this number. Let me write that down. I get 34336.806 newtons per coulomb, and this is right. The reason why it is right is because the electric field strength due to A at point P is to the right. Why is it to the right? Well, because A is positive and point P is on the right side of that, so an imaginary positive test charge will be forced away from A, which is to the right. We can do the same thing here now to find the electric field strength at B. Of course, the direction here will be down. The direction is down. Essentially, because B is negative and P is above it. So an imaginary positive test charge at P will be attracted to the negative source charge at B, which means the net influence would be down due to B. Probably shouldn't have said net influence. The influence due to B would be down. Let's see what we get now. I'm going to take Coulomb's constant times the charge of B, which is 25 microcoulombs. Remember, you never put negatives in. If a charge is negative, that negative doesn't go into the formula. That's just for us to determine directions on our diagram. 25 microcoulombs divided by the distance, which is 0.05, quantity squared. I'll just step back and double check my entry. It looks okay. So you get 1, 2, 3, well, I'll just write the whole thing down. If you're puzzled by the fact that it's got the same digits as Coulomb's constant, I'll leave it to you why that works out. It has something to do with the charge being 25 and the distance being 5 centimeters. Anyway, we get 899 followed by 5, what I believe is 5 zeros. 1, 2, 3, 4, 5. Yep. Now, the net electric field is found by adding those two fields. And I actually want to write this down. E net equals EA plus EB. But notice I'm not saying you add these numbers together. I mean, if I was saying add the numbers together, then I would have written this, and it would be absolutely wrong. That's not what we're talking about. We're talking about adding the vectors together. Adding these two, there we go. Adding these two vectors together. This vector plus this vector need to be added together. Well, how do you add vectors? You add them being aware of the direction. If the two vectors are in the same direction, you simply add the magnitudes. This goes back to Physics 20. If the two vectors are in opposite directions, then you take the larger magnitude and subtract the smaller. If they're not in the same direction and they're not in opposite directions, then you ask yourself, if I draw them tip to tail, will that lead me to the net vector? So I am going to draw these now tip to tail. I'm going to draw the vector to the right, followed by tip to tail the vector down. And the advice I've given you, this goes way back to Physics 20, is always draw the horizontal first. I don't know how well I've drawn these. If I compare these two numbers, I think the electric field at B is probably almost 3 times greater. So, if you're a stickler for a good diagram, maybe it looks like this. But the bottom line is this is the answer to the problem. The magnitude is indicated by the length of that hypotenuse, and the direction is indicated by that angle, which will be, assuming we're looking at map directions, south of west, or you could just say down of right, although that doesn't really sound right. So let's put the numbers on here. This is 3.43 times 10 to the 7, I believe. 1, 2, 3, 4, 5, 6, 7. This is 8.99 times 10 to the 7. These are both newtons per coulomb. I guess I'm being a little lazy by not writing that. 1, 2, 3, 4, 5. I'm just double checking my scientific notation. So, what is the magnitude of this? Well, I've said in Physics 20, even back in Unit 1, I shouldn't always have to write down every step here. You're going to use the Pythagorean theorem to find the magnitude. I'm not going to write that down. I'm just going to go for it on my calculator. I'm going to take that and square it and add this and square it. Pythagorean theorem says you square the leg plus the square of the other leg equals the square of the hypotenuse. So I hit enter, and now I take the square root to get the magnitude of 9.6 times 10 to the 7 newtons per coulomb. What's the direction? Well, we can't just say left, right, up, or down. I'm going to make this, I probably should change my note package so that it says this someplace. I'm going to assume that we're looking at map directions here, which means this number is actually west, and this number is actually south. And that means that we're going to get an angle of so many degrees south of west. Don't forget, tangent of an angle in a right triangle is opposite over adjacent, which means theta will be the inverse tan of opposite over adjacent. Again, I think finding the angle and the hypotenuse in a situation like this is child's play. It should be by the time you get to this point in the course. So inverse tan of opposite over adjacent. So inverse tan of opposite, which is the big one, divided by adjacent, which is the small one. I must still have it there. There we go. I think that looks okay. Oh, I better check to see if I'm in degrees. I might not be. No, I am. So about 69 degrees south of west. And that's all she wrote, 9.6 times 10 to the 7 newtons per coulomb at an angle of 69 degrees south of west. On a diploma exam or a unit exam, what they might do is, to avoid having to deal with the whole direction thing, southwest, right, down, all that stuff, is the original question, so I'm about to erase a bunch of stuff here. The original question might tell you that this is the net electric field, and they might ask you in a numerical response, say, just to determine theta. What is the angle in that diagram? And you need to recognize that for you to answer that question, there we go, you're going to need to determine just give me 1 second here. You're going to need to determine this vector and this vector so that you can add them tip to tail, and those two vectors are the two vectors that we calculated. So there's a number of ways that this can be presented to you on an exam. Anyway, the answer to that last example is 9.6 times 10 to the 7 newtons per coulomb at an angle of 69 degrees south of west. That angle is 69 degrees. Hope that made sense. That's it. In the meantime and in between time, I hope you have a good rest of the day, and we'll talk to you when I talk to you. Take care.